when theories change, sometimes there's revolutionary upheaval, but you have to have something better to replace it with, or you just don't abandon something without having something better. So in some ways, the pessimistic fallacy is this kind of broad-based skepticism that doesn't leverage any other knowledge. It just leverages skepticism, and in that sense, it's very asymmetrical. And you say, if you don't have something better to offer us, don't bother. Wait until you have it, and when it comes along, we'll manage it. That's how science works. The cost of discovery is the risk of error.
All right, so welcome everyone to today's interview, where I'm very pleased to welcome Dr. Douglas Allchin. He is an AAAS fellow and resident fellow at the Minnesota Center for the Philosophy of Science, and his work has focused primarily on history and philosophy of science. His books include Teaching the Nature of Science, Perspectives and Resources, Sacred Bovines, The Ironies of Misplaced Assumptions in Biology, and Toward a Philosophy of Error in Science. And that last book will be our focus for today. There it is. Nice. I'll include links to where people can find that at Amazon or OUP, wherever, and find bookstores elsewhere. But anyway, he also has various published articles on these topics and related things. So yeah, feel free to anything. But with that, welcome and thanks so much for being here, Professor Allchin.
It's a pleasure.
Awesome. So just as a brief introduction then, do you mind giving a bit of an overview of the book? What is it about, and what might people expect to get from it? Like, why might people want to read it?
Yeah. So we all admit that science proceeds through trial and error, but philosophers have really spent their time focusing on how the knowledge gets built and not so much on the error. So this is an exploration of that kind of shadow zone. And after the preliminaries of pinning down what an error actually is, because it's a kind of slippery definition, I go through a very standard procedure of like, what are all the error types? How do scientists make errors? And then how do they find them? How do they fix them and remedy them? And then look at some of the philosophical implications regarding things like progress, the nature of knowledge, uncertainty, and concepts like error repertoires, methodologies, checkpoints, things like that.
Yeah, good. So maybe we should start with just thinking about what error is broadly, like, because someone might say that, well, error is just like a false belief, right? And maybe you don't need anything more than that. But you think that that's not quite right, or you take a different approach to error. So maybe if you could talk a bit about why you think that's not sufficient, or why you think that's not the sort of, or how you would prefer to approach thinking about error itself.
Yeah. So it is true that mostly when we think about something that's wrong or an error, we think about the fact or the claim and the fact that it's false. And I've shifted the orientation to look not at the claim, but at the justification. So from my perspective, an error is something that we once accepted as justified, but then through the emergence of more evidence, later deemed to be that same statement as unjustified. Or conversely, what was once unjustified, we suddenly see it's like, oh no, there's justification for that after all. And that's interesting because it necessarily puts a kind of a diachronic spin on the concept of error. You can't be in error and know that you're in error at the same time. So let's take the example of Pluto as a planet. When was that an error? Was it an error when Pluto was discovered and it was called a planet? Well, at the time, nobody thought so. So it's hard to say that it was an error, even though we might say now, in retrospect, we would have said it was an error. And then by the time the International Astronomical Union decides, like, well, we're not going to call it a planet anymore. Well, by that time, it's no longer an error because everybody knows it's wrong. So it's gone through this odd transition. So it's the comparison between then and now, which is really at the heart of it. So we're talking about learning, we're talking about scientific change, we're talking about incompleteness of evidence and how we manage that. So that's the first way about thinking about error in a different way. And one of the things that comes along with that is that we often want to say that error is something that should or could have been prevented, that there was a violation of the methods of science, and that makes the person who made the mistake culpable. So a lot of our conceptualizations about mistakes and being wrong is very much about accountability. And I sort of point out in many ways, you can be wrong for the right reasons or right for the wrong reasons. So there's this kind of decoupling between methods and what we ultimately take to be true or justified. So we want to decouple this from what the person did to the nature of the justification and the structure of the evidence and the reasoning, et cetera. So those are two kind of major shifts, one from the claim itself and the other from the methods, and shifting to the nature of the justification, and that the justification changes much to our surprise.
Right. So you'd say that there could be an error in science, even if it turns out to be true, so long as maybe we just didn't have any warrant or justification for it. Would that still count as an error, do you think?
It only counts as an error when someone comes along later and exposes the error.
Mm.
So there's, if we don't know, we say, well, we don't know yet. We're in a status of uncertainty. But at certain times we say, well, no, we're going to accept that theory. And that's when we step into the zone of possible error, of saying, oh, well, I said it was justified in the past, but I don't believe so now.
So it's being an error is a matter of its being recognized as such. Like it has to be sort of uncovered that we lacked the relevant warrant or made some mistake or something like that.
Yeah. So this is the very interesting upshot, is that when you determine that there was an error, you know what the error was, you know that it's a form of knowledge, although it's a form of negative knowledge. So it's shifting from knowledge to uncertainty to eventually negative knowledge.
Right. Yeah, and that'll be explored further. Okay, but just quickly on the Pluto case, for example, mm-hmm. Like what exactly was the error? Like, I mean, correct me if I'm wrong, but wasn't that case primarily about like changing the category of planet or something? Like maybe there wasn't something in error before when people said it was a planet. Rather, we introduced a new standard for a planet based on, I don't know, some pragmatic concern about not having too many planets or something like that.
Right, but that is in a sense kind of the nature of the error. So we habitually say that one of our jobs of science is to cut nature at her joints. So if we decide that there is a natural kind called a planet, and in fact we still have a category called planet, we can be erring about how we have put the boundaries on that. So what's interesting is earlier century, after the discovery of Ceres, which was the first asteroid, it was included as a planet. And I think we would say, well, no, that wasn't the planet. But it only took them, many decades to realize, like, oh, there are other asteroids. This isn't the proper way to carve nature at its joints.
Yeah, fair enough. Fair enough. And then you also want to distinguish error from like uncertainty or like imprecision sometimes. So what's the difference there, do you think?
Yeah, so uncertainty is a matter of imprecision, of simply not knowing the answer. So we can look at the development of Hubble's constant, typical of many, many physical constants, where we're trying to get the right value. And over time, we get better instruments, and we're able to limit the number of values, and so we get more confidence in what the value really is. But then sometimes things come along with a systematic error. So one of the key elements in Hubble's work was looking at Cepheid variable stars. And they help to calibrate distances and therefore how far things are away, how large the universe is, how old the universe is. But Alan Sandage came along and said, oh, but these Cepheid variables actually have two different types, and the ways in which we calibrate the age and the distance from them is different. So now we have to incorporate that into what we just did. And when they did that, the age of the universe doubled. That was a pretty significant, that was outside the zone of like the standard deviation. And then many, many years later, there were a number of Cepheid variables that were deemed to be confused with nebula. And that, again, changed the very nature in which you thought about the structure of the universe, the way of calculating this constant, and the age of the universe doubled again. So those are systematic errors. Those are errors. And the others are simply uncertainties. So when you're confident about saying, well, I don't know, could be this or this, you haven't really committed an error because you've admitted you don't know. But if you say, well, we've ruled out one, or we've decided that this is the value, then you've committed yourself. So it's very much related to your epistemic posture about how much confidence you have in the justification that you've produced.
Yeah, that seems reasonable enough. And then perhaps it's important, and this comes up later in the book more, and maybe we'll discuss it later as well. But if you're giving this sort of account of error tied to warrant and justification and stuff like that, maybe it's important to think about that a little bit more. So like, to what degree do you think this connects to like broader issues in epistemology, how we think about like what knowledge is and like the conditions of justification and so on? Is that an important factor here, or what do you think?
Well, we can talk about the whole nature of what knowledge is if we're including like false beliefs, if they're justified as being a form of knowledge. I think one of the interesting areas that hasn't quite been fully explored is, what does it mean to have completeness of an argument? When do you consider your justification complete or sound enough to make a judgment? We all know that we can make models, and that models are incomplete, and that they can be shown to be false using other models or more complex models. But I don't know if we've really explored the notion of when do we reach that point. Interesting parallel perhaps to Gallison's questions back decades ago. When do experiments end? When do you decide that you've proven this to your satisfaction, collected enough evidence, and we're done. We publish, we declare it, and we move on to other things.
Yeah, I wonder. I mean, I'm inclined to think that for many of those things, not just like when like we're satisfied or when it's the sort of enough for our whatever practical purpose we might have. Some of these things are kind of inherently vague and contextual and variable, right? But even whether we have support or whether we've made an error in the sense, that could also be vague, it seems a bit to me as well. So I don't know if you want to comment on that. Do you think there might be vagueness in some of these things? Like, not just vagueness as a matter of uncertainty, but vagueness as a matter of, well, we're employing these sort of imprecise notions that don't decide like a precise boundary, if that makes sense.
I suspect that when we get to that level of understanding completeness, it will be about degrees of confidence, not necessarily in a statistical sense. But you often hear when journalists report new scientific discoveries, they'll say, well, they'll consult other experts outside the experimental team, and they'll say, well, this is a very sound thing. It was very promising. Of course, we haven't explored this, and we haven't checked that, and we'll need to consider this further. So those are all the qualifications that kind of, I think, in what you're saying is provide a boundary for the confidence or the stability, reliability perhaps, of those conclusions. And I suspect that the more we pay attention to error, the more we will be sensitive to making those statements and including them as part of what the statement is itself.
Right, fair enough. I guess one of the things I'm just, I guess the confidence and such will come in degrees, but like maybe there's no like precise point at which like, oh, and that's sufficient to like demonstrate the case, or now we don't need to do any more, experiments or anything like that. I mean, maybe in a matter of practice, we might just happen to decide at some time that we're not going to do any more, or we're satisfied with that. But like, I don't know. It's not like I think in principle there's some precise point at which like the correct amount has been done or something like that. You see what I'm saying?
Absolutely. So this is the long-standing conundrum of induction. When have you found enough cases? When is your, in Goodman's language, when is your swatch representative of the whole? And I think we know now that it's nigh on impossible to say that we've reached the end. And I think metaphysically, we're still going to keep arguing about, are we converging? And do we need to converge even for there to be growth of knowledge? And then outside philosophy, from a policy perspective, there are plenty of opportunities where we don't need to know for sure. We just know enough to act on it. We have enough confidence in climate change now that it would be imprudent not to do something about it. Even though we don't know the exact degrees, there are a lot of contingent factors about recent study of the ice sheet on Greenland and what that may do to sea level. So we only perhaps need certain levels of knowledge to be able to get us through. And that takes us into the whole notion of heuristics and the imperfections of knowledge. But that doesn't mean that the knowledge isn't valuable and we can't act on it.
Yeah, that seems fair enough. So then thinking about, I guess we could move on to sort of that's different sorts of errors and how to categorize them. So you talk about a sort of first layer of map. You separate into sort of layers of the sort of connection between the scientists and the world, so to speak. And so on the first layer, you have the connection between the sort of raw data and how we represent those, something like that. So like, sorry, no, it's the connection between the raw data and the world that they're meant to represent, or something like that. And the first layer of errors occurs when they don't faithfully preserve the structure of that or the details of that, something like that. So maybe I didn't express that perfectly well, but could you maybe say a little bit more about this category of error?
Sure. So let's take one step back and look at the large picture. So when we think about a justification for a theory, it's a very, very complex layered thing. It's not just a matter of a few assumptions and a few pieces of data. We can imagine this hierarchy, tree structure where all these things are built But ultimately, in science, we're accustomed to rooting those arguments, some assumptions, but we want to really focus on the data and the observations. So if we think about this, how do we go from those layers, those inscriptions in Latour's language, to combinations of inscriptions, to patterns of those things, to models, to theories, and then get a consensus across the community, the scientific community, that those interpretations are correct. So for convenience, it's helpful, I think, just to separate those out between observations, observational errors, conceptual processes, various forms of reasoning, inductive, deductive, abductive, metaphorical, natural selection, method of difference, etc. And then finally, the social or discursive level. So to go back to the observational level, we're looking at the kind of question is, are we looking at what we think we're looking at? So there may be a contaminant, in which case we're getting the wrong picture. There may be a confounder that we don't know about. We haven't controlled for it. So we're getting an incorrect signal. We may be using an instrument, and the instrument may be doing something. So there's a fascinating example of a retraction from Science several years ago, where they were measuring the diamagnetism of a sample. And the retraction came along later and said, well, we were not measuring the diamagnetism of the sample. We were measuring the diamagnetism of the instrument that was holding the sample. So there had been this blind spot based on the use of the instrument, which had become invisible. And then later they realized that things weren't working, and they were able to isolate and track down the error to the instrument itself. So there are all kinds of instrumental artifacts, highly repeatable. And of course, our own human observational skills are not perfect either in terms of our perceptions or in terms of seeing without bias. So there have been a number of studies now about observer bias, and things as unsuspecting as trying to measure the amount of foliage in the trees in the tropics to measure how much is being defoliated. Well, it turns out that if you know what hypothesis you're testing, you're actually biasing your estimate of the number of leaves that you're looking at. So they now have controls for observer bias there. So these are all examples where you're not looking at what you think you're looking at, and you don't find out until later when you get caught up on something.
Yeah, good. And I guess you covered a fair amount of the examples you go over in the book, although, of course, you can suppose that there could be more, but yeah, you might think that you could have a contaminant, and that could affect the result, or different things with the instruments, as you mentioned, or observer bias, which will be important. We'll get into stuff how you can mitigate that, or you can have blinded studies and so on. I don't know if I want to say anything more about any of those particular examples.
Let me add one more, which I don't think philosophers have given due attention to, and that is the role of heuristics and proxy variables. So the world is complex, and it's often inaccessible, and we can't measure what we really want to measure. So we choose something which we think is going to be close enough and will get us the answer. So there was a study in the 1980s about the relationship between high voltage power lines, electromagnetic fields, and the occurrence of leukemia. Well, it was nigh on impossible to fund a project that would go into people's private homes, measure their exposure to these fields, and then correlate them with the individual incidences of leukemia in those households. So they used wisely, as it seemed, a surrogate. They had what were called wire codes, and that is they knew how far these areas were from the power lines, how much voltage was carried on the power lines, and so they could use those values as a way of approximating what they thought was going to be the actual exposure. And as a result, they found a correlation between leukemia and electronic fields. Well, this controversy went on for 12 years. They went back and repeated the study. Many of them used the same wire codes over and over again because they didn't have the money to do anything else. And of course, that didn't help resolve the issue. And when the National Research Council finally got involved in the 1990s, they had the funding and they went out and they measured it. And they found out that the wire codes was an assumption that turned out not to be appropriate. It was a good heuristic. In a lot of cases, those things work out just fine and we don't notice them. But when things go wrong, we have to go back and say, let's make sure that we got this correct.
But the heuristic stuff, like the heuristic gaps, that's an example of kind of level 2. That's a conceptual error, or right? If I recall correctly.
Well, in this case, it was an assumption that was made in the process of collecting the data. So the data they collected about the wire codes did not coincide with what they wanted it to represent, which was the actual values of the electromagnetic fields.
So would that count as a kind of like a framing error then, or something like that?
It can be, yeah. So that some of the examples that you're looking at will fall within that category, but some of them won't. So you need to be, so anything where you start talking about false positives and false negatives, you're using some kind of a heuristic or a rule, and you know it's imperfect. And as a result, sometimes you're going to get a signal to your home pregnancy testing or COVID testing thing. And in some cases, you'll get a false negative. So there's a displacement or a misframing of the observation. And in some cases, we have ways of just digging deeper. So here's another interesting example. Dave Keeling, who did the Keeling curve measuring atmospheric carbon dioxide, when he started out, he collected samples in these large fat flasks and went through the chemical procedure of, in a sense, reacting with the carbon dioxide to find out how much was there. It was rather time consuming. But he learned that carbon dioxide absorbs infrared heat. So he did a little research, put a little device together. And so now most of the measurements are done by exposing the air sample to an infrared source, comparing it against a standard source, and finding out how much of the infrared light is absorbed, and therefore inferring indirectly how much carbon dioxide you have. You're not actually measuring the carbon dioxide directly, you're measuring it through a surrogate variable. But it's completely trustworthy at this point. It's been used over and over and over again. And if they do take the longer, slower methods, they always coincide. So that's a heuristic method that works.
Right. But the fact that there's that sort of extra layer of separation between the direct observation and that's taken to imply introduces potential errors, right? Because it could be that your heuristic fails in certain cases, and that's right.
It's a qualification, which means you have to calibrate your instrument, check it from time to time. And they they still occasionally collect raw samples and do the analysis on those as a kind of a backstop to make sure that they're still working. At this point, again, they know most of the errors that could crop up, and they can check for them and rule them out. So that's our backstop in a sense.
Right. And maybe you sort of already hinted at this, but thinking about errors in terms of, well, there's a kind of first layer, second layer, third layer. I mean, it's not like what goes wrong in some instance might be like, sort of fall under multiple different categories, right? I mean, there might be different things involved in the error. That's not just,
it's quite possible for there to be like a local error that's part of a more global error. Sure.
Yeah. Right. And then, okay, I guess we could talk a bit about the kind of second layer, what we call like conceptual errors. And can you talk about how this forms a new layer that can introduce new errors beyond like the stuff from like the basic observations or something like that, the raw data?
So the area of looking at the quality of observation is very much part of the new experimentalism and experimental philosophy. But there are times when we see various epistemic hurdles and we solve those, and we have what we consider to be reliable observations. But that doesn't clear us because philosophers are quite familiar with all the kinds of logical fallacies, many of which parallel cognitive biases or heuristics. And as a result, the fact that they're kind of like hardwired into our brains means that we're not always aware of them. To the degree that we are aware of them, we've been taught about them. And so we go back and we check, let me make sure I haven't done this and I haven't done this. Oh, let me go check with another person to see if they've looked at it the same way that I have, et cetera. So there are all those things like confirmation bias. About when we have an observation, we say, oh, that's enough. And we'll cut off the observations when in fact it may not be enough. But statistics gives us a good check on that system. Another kind of conceptual error is overgeneralizing. So we take an induction and we just take it a bit too far. So Boyle's law is great. I love Boyle's law. But it turns out that when you get to very, very high pressures, say over 10 atmospheres, that beautiful relationship breaks down. When you start lowering the temperature, the gases begin to act like a fluid and the law breaks down. Some people now know this as the ideal gas law, and that's because it only works for, quote, ideal gases. You have things like ammonia gas or methane or carbon monoxide. Again, there are things that at certain extremes, it doesn't work. So as long as you circumscribe the scope of Boyle's law, it's fine. But it's interesting that we call it a law in the sense that it's universal when there are all these qualifications and restrictions, boundaries that we put on it.
Yeah, and for overgeneralization, Paul, quickly, you want to say that's not just the same thing as a hasty generalization, right?
We could see that they're related. Overgeneralization is usually about how far you extend the domain of your conclusions, whereas a hasty generalization might simply be the result of not checking some key assumptions, finding a confounder that you hadn't thought was there, and went, I just acted too rationally. So this is also a place where we can start thinking about some of the things that have plagued the philosophy of science since the work in the sociology of science, showing all the biases that scientists have. So gender bias, religious bias, class bias, racial bias. These are all ways in which our minds play tricks on us. Again, they will lower your standards for what is considered to be a satisfactory justification, if you happen to agree with the conclusion, and they will sensitize you to being a little bit more critical of evidence that is not in accord with what you're expecting. So it's a kind of a broad expansion of confirmation bias.
Yeah, good. That comes up where you talk about. Well, those are cases where those different values and commitments and so on, be they religious values and commitments or biases regarding race and gender and so on. Those are just further examples of confirmation bias, right?
Yes.
Or do you separate it? Yeah.
Yes, but it is sometimes helpful for us to know where is that confirmation bias coming from. In some cases, it may be because we simply encountered one observation first and expected others to follow that without any major overtones to that. That's in a sense the very first layer of confirmation bias, literally confirming. But it may also be that there's theory ladenness. It's not just about a bunch of observations, it's a whole set of observations and expectations that you make. And I think it's valuable to talk about those separately, because we tend to draw this like little dotted line around science in the lab, suggesting that those are the only things that will matter. But we all know that scientists are human. They are members of culture, and they bring those elements of culture with them, along with their own backgrounds, their biographies, historical exposures, into the lab. And those are sometimes harder to detect. So the ways in which you would have to expose them, in a sense, would be to find someone who had a different gender or a different race, to sort of say, I don't think that, from my perspective, I don't think that step of reasoning is sound. And that's, of course, a major part of the explosion in social epistemology over the last 2-3 decades.
Right, and you mentioned the theory ladenness case there. I recall was the case with Da Vinci and connecting the spleen to the heart. Was that an instance of that, where the idea is that because there's this sort of background or implicit theoretical commitment, there must be something carrying the black bile or whatever it was, that there must be some connection there. And so even though it wasn't observed, like he just added it in anyway or something like that. That's a sort of bias from theoretical commitments or something like that.
Yeah, it's a great story, because we know Leonardo was a consummate draftsman and knew how to draw accurately. And we know that he had good powers of observation as well. So when we see, he's dissecting corpses and he's drawing them, and he draws this little channel, this carrying presumably the black bile from the spleen to the liver. He drew it. Why? We don't know why he drew it. But it was in Galen's philosophy. And we can just imagine that Leonardo was going, I just must have missed it. I wasn't careful enough in my dissection. I know it's there, so I'll just draw it in anyway. And it's fascinating to look at these drawings, which are centuries old, and go, oh, that's in a sense evidence of confirmation bias.
Right. And sort of related, I guess, maybe it's not a confirmation bias or theory-laden judgment, or maybe it is the where you talk about we're just having a faulty assumption can lead to error. Like I recall the case with Lord Kelvin, and where he measured the cooling rate and inferred the age of the Earth based on that. But he didn't actually, he sort of implicitly, or maybe perhaps it was more explicit, assumed that there wasn't something producing heat in the Earth, and it turns out that was false. So I guess that's a different type, or maybe that's sort of like the theory-laden judgment case again.
We can imagine that Lord Kelvin was really genuine in trying to determine the appropriate value of the age of the Earth from its cooling rate. he did have some preconceptions, but we don't see any evidence that those, in a sense, guided his assumptions. But in this case, he made several assumptions about the structure of the Earth, about cooling rates, and his deductions and his calculations were all correct based on his assumptions. But the assumptions were wrong. He didn't know about convection currents inside the mantle. That changed the calculation immensely. He didn't know that things would be, the cooling of the crust would have a major impact on how the temperature was flowing out. And that had a major impact as well. So those assumptions became rather obvious at the end of the century, and Kelvin they were exposed to Kelvin, and he kind of smiled like, well, I said it was assuming that there were no other sources of heat. So yeah, there could be just simple assumptions that you make for the sense of convenience, necessity, or lack of collateral knowledge. You just didn't know enough about the structure of the Earth at that point. What was he to do? But again, this is an interesting example of the completeness of knowledge, where what he didn't know actually mattered.
Right. Yeah. No, it's not so crazy to think like at the time, maybe they just thought the Earth was a big rock, right? And it's like, well, it's not going to have a further source of heat or something that would affect these measurements. So it's just going to be a big rock cooling down over time. But yeah, still.
It's a good approximation.
Yeah.
But it turns out, in fact, that the whole thermodynamic calculations are so complex that no one uses them anymore. We rely on radioactive dating because we know that that's a much better method now.
Right. And maybe one more from this category here. You also talk about did you talk about how we're often like satisficers when looking for explanations or things like, well, once we find an account that's good enough, or maybe something that just looks right, we'll stop looking and we won't consider other alternatives or test it further. And then that's can lead to a sort of error as well. Right. So what do you think about that case, like the unaddressed and cryptic alternatives is one of the categories that you talk about?
Right. So this is an interesting a challenge again for how we think about philosophy, because we know from psychological studies that our minds work on not finding necessarily the best solution. We just finding a solution, one that's adequate to the purpose. And so if we collect data and all the data is consistent with the other data and it's consistent with our theory, we have coherence. And that's usually where we say, okay, what else is there? And so we declare ourselves, in a sense, done. But we find out later that there are some other ones. Daniel Kahneman in his book talks about our cognitive disposition. What you see is all there is. And so if we want to improve science in the long run, we might be more aggressive in looking for those other alternatives and trying to imagine them. And that's sort of like a layer of how do we make science better based on understanding error. So that might be an element of error analytics, which I imagine we could talk about more later.
Yeah, for sure. Thinking about that, like the fact that we often do that, where we'll look for something good enough or maybe not consider alternatives when we, seem to have something that suffices. Like that's a sort of heuristic in itself, right? Or it's maybe we often think it's just more efficient or more likely to work out just to expend resources elsewhere rather than spending more time on this looking for something else that might be there might be a better answer or something like that.
There are pragmatic considerations based on how much money you have. Absolutely. But we should point out that often people are not satisfied. We do a preliminary study on drugs, and when we get good results, then we say, well, now it's worth investing the resources in doing a full-scale clinical study. And you do that, and perhaps the drug gets approved, but they're now obliged to keep on collecting data. So in the case of Avastin, breast cancer drug, they collected data, and 2 years later they had to take it off the market because there were enough side effects that became visible that just hadn't shown up in the limited sample, even though it was a sample large enough to get the drug approved. And in the same way, particle physicists, they're pretty content with a standard model now, but that doesn't keep them from trying to get better measurements, looking for all the particles which are supposed to be there. And there was a interesting finding about the mass of the W boson a few years ago that was clearly outside what people had measured earlier. And it was I forget which group it was, but they were respected. It was a highly respected study. And oddly enough, the physicists were celebrating the fact that that they had gotten the weight of the W boson wrong, apparently, because this, they said, would be a clue to more advanced knowledge. And then after several more studies, a couple of years later, they kind of zeroed in and said, well, no, it wasn't that after all. So we're stuck with the old standard model. But it's interesting that they're so willing to take it to the extreme, to test it, to make sure that it really is as rigorous as we want it to be. So increasing the levels of rigor is one of the things that scientists like to do. That's a epistemically sound kind of way of checking against those alternatives.
Right. Although sometimes that checking is a matter of, well, the stakes involved or what, other sort of pragmatic concerns, especially with stuff like drugs. Well, we really want to be sure that we have a safe drug, perhaps, before we start giving it to people because of the effects that it could have. But yeah, maybe that's a sort of good pragmatic encroachment.
This is interesting because our standards of proof change over time. So Leon Lederman was looking for a new particle and found it. I forget, it was the p-value is 1 in 10,000, 1 in a million. It was pretty low. But they went back and they did more study because they're physicists and they do that. And they found out that this little blip in the energy levels sort of smoothed itself out with more samples. So what had been named the epsilon particle turned into the Oops Leon Lederman particle. And as a result of that, physicists knew from there on not to use 1 in a million chances. It needed to be 1 in 10 million or more. And that changed the practice to consider what standards of proof really were. And that was based on experience, based on history.
Right. And we can now talk about 5 sigma, 6 sigma, or whatever, that sort of thing.
Yeah.
I did want to also mention about a case with, and this might draw connection to some of the benefits of errors, but when physicists especially think there might be some mistake in a accepted model, that's one of the most exciting potential discoveries, right? Because it might reveal, area for future research, a potential new research program and so on. But that's, and also, I guess if you show something that's commonly accepted to be false, that's you can get a lot of notoriety from that. Although maybe that's not a good thing in its own sense.
Well, it's interesting because if a discovery is something that's really original and surprising, it's because we didn't expect it, or it contradicts our expectations, in which case we are relearning, not just expanding. It's a discovery, but it's relearning, and relearning in a sense involves unlearning. So the same thing happens in biology numerous times. Crick and then Watson enunciated a version of the central dogma about the relationship between DNA, RNA, and proteins. And then retroviruses were discovered that produce RNA, DNA synthetase. Well, that was just a bombshell. But it was also exciting. And when we find out about ribozymes, those were exciting. So all these discoveries upset the canonical views, but they're also deepening our levels of proof and expanding our horizons. So we normally don't get too upset when when we discover certain errors.
Good. And I should mention the sort of third layer here of types of errors before we move on to, or cover further some of the broader issues. So when you can also have sort of what you call social level errors that are introduced not by individuals like alone, but because of broader social phenomena like communication, institutions, trust, and so on that might come along with that. So can you discuss that a little more and how this, maybe some of the examples of this?
Yeah. So we've entered a zone now of acknowledging the significance of social epistemology, that there is a level of vetting claims at the social level, of overlapping backgrounds, different kinds of assumptions, using those assumptions to your advantage, interpretive perspectives or standpoints, different genders, different races. So Robert Merton back in the 30s started talking about this level of producing knowledge at the social level and providing a set of norms, methodological norms, about the fact that all the results would be open to everybody. Science would be communal. Everyone would be considered an equal voice in the discussion. There would be universalism. And of course, we know that's not true. Lots of scientists have much higher credibility than others. And that there would be general mutual skepticism. And that's that key element to being able to expose some of those theoretical biases, confirmation biases, etc. So from my perspective, at least, if we assume that science is supposed to be able to root out those biases because there are different biases across the community, if the community is homogeneous and all believes the same thing, then they won't be able to root those things out. That's communal confirmation bias or communal cultural bias, which is of a different kind, I think, than just the individual error. So J. Harlan Bretz, not a very distinguished geologist at the time, went out to study the really remarkable geological formations in eastern Washington state known as the Scablands. And everywhere he looked, he saw geological evidence of water flow that would be familiar on a small scale, but he saw it on this monumental, huge scale. And the only conclusion that he came to was that there had been a huge flood that had shaped this basin. And he went back several seasons to collect the evidence, much to his own surprise and dismay. But the many of the members of the U.S. Geological Society, or USGS, had a symposium in Washington, D.C., where they invited Bretz to present his findings, and then basically ambushed him and all these very noted geologists just trashed and saying, uniformitarian is the rule. We know this, and therefore your results must be wrong. None of them had done any field work. None of them had actually gone out to look at the observations. And that is a form of, in a sense, making a conclusion somewhat blindly. And it was done because they all agreed with each other. So that's a very nice example of communal confirmation bias. And when other geologists in their expanding horizons went out and observed the scablons, they saw exactly what Bretz did. And 30, 40 years later, they sent him a tribute, said, no, you were right all along. So, but it took a while.
Yeah, I like that example. And one of the other important ones in this section is like publication bias. Not even just like which things get accepted, but like which things are sort of considered legitimate areas of study, and what things are funded, and other things like that introduce biases on a more social level. So yeah, I don't know if you want to say anything about that as well.
I want to acknowledge them and point out that this is now an area of active concern and discussion among practicing scientists, and what is known as the reproducibility crisis. The open science movement really urging the fact that we have access to all this data so that other people can interpret the data, that you have open code so that people can check it, that we publish negative results, the file drawer problem where you doesn't have statistical significance, it's not going to get published, so you just stuff it in the back of the file drawer and it disappears, when in fact, when you do a meta study, the fact that there is a negative results actually proves to be immensely, immensely important. So this is an area of really active concern right now. So anything I could say would probably be out of date in a week.
Fair enough. Yeah, part of that seems like almost, it was very difficult to overcome some of these issues to a significant degree. Because a lot of journals and so on aren't really that interested in publishing more negative results or stuff, just like confirming stuff that had already been studied, that sort of thing. Because it's just, it's probably not going to get cited that much. It's maybe not very interesting. So I don't know. And then people who do that are less likely to get more funding for that research. Like, people are more likely to fund something that might find something new than just like checking something that's already been fairly confirmed. And it's not so easy to overcome that because of just like financial incentives and other things like that.
Yeah. So how much replication we want to do just for the sake of replication is a unanswered question. Most of the replications that have been important historically, from my perspective, have been ones where people were trying to build on the results. They weren't trying to check them. And they tried to build on them and it didn't work. And so they had to go back and find out what was wrong. So that's a kind of a separate question. David Hull gave a really nice treatment of this in his book, Science is a Process, about, what motivates us to discovery. And he understood at least that if you can challenge an accepted theory and show that it's wrong, and you have the evidence, well, in fact, that is publishable. It's this gray zone of like, I tried, but I got the same result. So again, we're beginning, I think, to the values in science are beginning to change. There are some journals, of course, that publish negative results exclusively. And we have communication problems, even with things that have been shown to be wrong and been retracted. And so we have the website Retraction Watch. It's not exhaustive, but it's making an effort at least to be out there. So I'm certainly hoping to rally some interested philosophers and scientists to talk more about how we institutionalize our documentation of negative knowledge, negative results. How do we make it searchable? How do we make sure that it becomes important for people who are, doing a literature review to know that there is 3 replication efforts that all failed? Because again, many of those don't get published because for all the reasons that you meant. But the scientists themselves are chatting. They say, we don't like the promotion, how our job evaluations are done. We need to change this. So the discussion's active. Let's watch what happens.
Right. Yeah, I'm not sure we're going to make much progress on that here, but yeah. And then maybe 1 or 2 more from this section, and we can discuss some of the broader issues. Well, another important one has to do with misinformation, or where there's conflicts of interest, and people or groups or companies sometimes end up, for their own benefit, trying to make people misinformed or make the science less certain than it perhaps should be. You can give examples from the tobacco industry and so on about this. And I guess that could come not just by having studies published that seem to indicate alternative results, but by withholding data that they might have. And I think there's some history of that as well. So yeah, I don't know. Maybe this is another thing where we start to disentangle it from a sort of personal interests and other pragmatic concerns like that. But I don't know, maybe if you want to say more about this one.
So I think this is going to be one of the key institutional issues moving forward. We now know that conflicts of interest are important. And many journals over the past 10, 15, 20 years have instituted declarations about conflict of interest as a standard part of publishing the paper, sometimes even beyond science itself. But that doesn't mean that people don't lie or hide things. So that's going to be another challenge, is checking those statements themselves. But so the interesting example in the news currently, which obviously didn't make it into the book, was the study of the safety of glyphosate, Roundup, as a weed killer. And now we find out that the data was essentially falsified and used to get the approval of this pesticide. And we'll see if the current data is enough to leverage a change in policy. I think from the perspective of most of the scientists, it should. But we're facing challenges there, which is interesting because we can look at conflict of interest at 2 levels. One is within science and the ways in which scientists are misled because of conflicts of interest. So there may be ghostwriting, using a respected author for what is ostensibly an industry study, and somebody just signs off on it and gets paid for it. Lots of examples in a book by McGarity and Wagner called Bending Science. Frequently, again, industry and commercial interests trying to make organic farming look bad, or trying to promote red meat as not so unhealthy as they said, or the Lawn Institute trying to convince people that turf lawns are eco-friendly, when in fact they're actually, with over-fertilized, they end up producing so many bacteria that produce nitrous oxide that they're contributing rather significantly to greenhouse gases. So there's all those cases that happen within the scientific literature, and we should at least acknowledge that there are ways in which many of these same sources try to misinform the public by dodging the science. They just try to present the science to the public and say, do your own research. You decide. You're not an expert, but we're going to let you, use our cherry-picked data and our misleading arguments. And obviously, as a result, you'll come to agree with us. So that's a conflict of interest that's shaping misinformation in the media, which is on a whole different level than misinformation or deceit within peer-reviewed science. So right. Yes, a significant element. And again, the more we raise our awareness of it, and maybe if philosophers start shaking their fists, we'll be outside the halls of legislature testifying and saying something must be done.
Yeah, and that some of those problems you hint at there as well, like where people can get mistrust of experts, of science, or of the institutions generally. That's a sort of further problem as well.
Yeah, so I'm for the sake of this book, errors in the media, even if they involve scientific claims, are a whole other matter of consideration, even though there is, in a sense, many epistemic questions. But the epistemic questions are largely about the transfer of expert knowledge from experts to non-experts, as opposed to the creation or development of knowledge within a community of experts.
Right. And sort of relatedly, you talk about fraud as well, and you talk about as more of a sort of social or institutional failing rather than just, I don't know, an individual moral failing or something like that.
Yeah.
So maybe if
I have a very atypical view on this matter. Most people will say that fraud is a matter of dishonesty. That was what the error was. Somebody just lied. And I look at it from the social perspective and said, but you trusted them. Why did you trust them? That was an error in a credibility judgment. And credibility is one of those heuristics. You don't have time to read everything, to redo every experiment. So we have this very nice system where somebody's past performance ends up being a basis for believing what they say next. So that became particularly significant in the case of the erstwhile discovery of element 118 at Lawrence Berkeley Laboratory. The guy they brought in, Ninov from Germany, knew how to analyze the data. He wrote the computer code and was able to assemble all the decay results to show that they had, in fact, presumably discovered element 118. Well, nobody else could get this result. So they went back and they tried to do it again themselves, couldn't get the same result. There was, over the course of 4 years, there was one external panel review, a second external panel review, a third external panel review, and a fourth external panel review, showing how truly exceptional this case was. And what I find interesting is that they eventually tracked it down to the fact that Ninov had gone in, manipulated the data files, changed the order so that he could get the predicted decay signature. And the external committee obviously faulted Ninov for doing this, and he was dismissed institutionally. But they also faulted the rest of the team for not having anybody check his work. In a sense, they criticized them for giving him too much credibility and making, in a sense, that allowing him to be a weak link in the chain. So that sort of coincides with my views, like, be careful who you trust. Know that the trust is well-founded. And in a sense, in some cases, especially where it's really important, you have somebody else run the program, write a different program, cross-check the results. So right. Credibility.
Yeah, so that I guess relates to a couple of the other ones from the social category. Like, well, first of all, the sort of checks and balances and stuff that we normally want in our scientific procedures might not have been functioning correctly there, or like, or maybe then there's the other case where you give too much leeway to some authority, or the wunderkind example. So yeah, I guess part of the reason is, okay, there was a fraud that happened in the sense that, well, somebody manufactured false data or something like that. But the fact that there was an error there more broadly was more than just that he typed those things on the screen, but that there weren't the relevant checks and people let that go through and so on. So in that sense, it becomes a social thing.
Yeah. And it resonates with what some of the sociologists, particularly Steve Shapin, have been telling us, that science involves a lot of trust. You expect that a published result has been done competently for the most part, and you may disagree with the interpretation of the results, but to a large degree, you don't go back and say, oh, I should do that myself, which is what they might have done in the late 17th century. They said, oh, well, let's do that. But experiments were simple enough and cheap enough then that they could sometimes usually do that. So I think we're learning now more about the conditions under which the checks and balances need to be exercised at a more micro scale within certain research teams, et cetera. And again, this is all about improving the quality of science over the long run based on our learning from the history of errors.
Right. And then that's also when we move on to thinking about, okay, how do we identify or discover errors? Well, it seems like one of the biggest things is, well, understanding what sort of errors that have been made or that we could make, and the sources of those is like one of the most important things, I would think. Do you agree with that?
Yeah. So there are two ways in which we can look at this. One is, as research proceeds, somebody doing a totally independent study may come up with results that don't agree with yours. So there's an incongruency, or in this case, a discordance of data. And then you have to figure out, like, so why is there a discordance? One of us or both of us may be wrong or partly wrong, and we need to reconcile these results and find out what was wrong. So this means the whole laboratory apparatus has to shift from looking at the discovery to tracking down the incongruence and isolating the error. And I think it's a very common procedure. Troubleshooting in a lab happens all the time, and philosophers really haven't spent enough time delving into that level of practice. But having awareness of the kinds of errors that can be made is a way of like creating this checklist. Like, did we do this? Did we do this? Did we do this? Let's check that. So if you're looking for an error, having an exhaustive list of the kinds of errors that might be made is a skeleton for probing those errors. In other cases, you might have the results and not encountered anything that's wrong yet. And yet you can use those error types like, okay, we did this, but it was based on this heuristic. Let's go back. Now that we have a positive result, let's go back and do the long form. We won't use the heuristic. We'll do the much more complicated thing to make sure that our heuristic was working properly. That's a way of using the errors as a guide to probe or deepen the reliability of your knowledge. So those lists of errors, I borrow the term from Deborah Mayo, error repertoires.
Right.
So these are the kinds of errors that are commonly made within a particular field. And people learn them indirectly as a result of their graduate training. But I imagine that if we were more explicit about it and had a label for it, it might be a more effective form of training scientists to say, okay, here's another one for your error repertoire, Julie.
Yeah, good. Yeah, this is the stuff that comes up when you talk about like the error analytic stuff. Like, yeah, you have the error repertoire, then maybe there's like certain signatures for certain sorts of errors, or when you use something that might result in one of those errors in principle, like you could develop a checklist for identifying when maybe you've made an error, things like this that you can use to, help identify errors or mitigate them, or confirm that you haven't made them perhaps as well.
Right. So
Yeah.
you mentioned error signatures, which is another layer of sort of understanding that our knowledge of errors can be used in a positive sense. So it's not just that you get confusing results. You may get a result that you recognize as saying, oh, that's a contaminant. So I had a friend who was working on superconductivity, and they produced a new sample, and it seemed to be a high temperature superconductor. And they published it, announced it, and then did some more research, and they were getting anomalous results. And it was the postdoc's advisor who went back to look at one of the spectrums and said, oh, that peak isn't sharp. That looks like an impurity phase. And then that in turn led them to find out that the manufacturer, which had given them 99.9% pure hafnium, was in fact contained 2 to 3% zirconium, which easily accounted for the results. So the fact that the advisor knew that how to read an erroneous data output helped them discover what the error was. So I think that, again, this is going to be an area for further research. And I know a grant project that's getting underway in the UK to try and talk about not just developing error repertoires of acknowledging what the errors are, but do they have a particular signature that identifies what kind of error has been produced? That shortcuts the process immensely.
Right. Yeah, that's fascinating. And maybe moving back to just, I guess we've started talking about the same thing, but about uncovering or discovering errors. Like you talk about how there's different, like in particular cases, you might have like a discordance or an anomaly or an ambiguity in the data. So I don't know, we could talk about some of these briefly. So like a discordance is when there is a conflict between different observational outcomes, like they should be the same. Maybe at some particle accelerator, they measure this and they do the same thing again, or at a different one and they get something different. As a sort of discordance that could indicate there's some error that's been made at some level. I don't know if you want to add more on this.
So we can talk about these mismatches where the coherence that we've produced that gave us confidence everything is okay breaks down. So two sets of observations may not be in accord. A observation may not be in accord with theory. That's a conventional Kuhnian anomaly. Or there may be different interpretations of the same data. So theory versus theory don't coincide with each other. So there's all these different ways, and they can all lead to discoveries at different levels. So simply the fact you have discordant results may seem like, oh, well, we'll just resolve this and then we'll be done. But when Raleigh was looking at the atomic weights of nitrogen and was using two different methods to make sure that he was going to get the right result, he didn't get the same result. And he didn't know what to do with that. So he had to do some poking around. But eventually, the fact that there were these mismatched atomic weights eventually led to the discovery of argon. And argon, in turn, led to the discovery of neon and xenon and helium, and a whole new column for the periodic table. So simply the fact there was a mismatch on some data results had enormous theoretical implications when you followed them through. So discordances of data are the first level of things. And sometimes it's just like oh, well, we were able to track down a contaminant. Well, and then it's easily dismissed. But
right, but sometimes it's a case where, like, it's nothing about that, but something about the circumstance was different when we thought it would be an irrelevant difference, but it turned out to be a relevant one.
Yeah. And again, this is what when people do a replication, you get discordant, and they say the replication fails. Well, people often want to imply that the original result was wrong, but it could equally have been the replication that was wrong. So if you look at it symmetrically, it's simply a discordance, and you need to then track down where that discordance came from. And in some cases, it may be that the original just made some assumptions that were totally wrong. In the case of cold fusion, it's like, oh, if you put a thermometer in a particular location and you don't stir the fluid, yes, you can replicate these results. But who wants a result from calorimetry that doesn't mix the fluid and only puts the temperature probe in one place that doesn't really tell you about the temperature of the system? So in those cases, the discordant results help to expose the utter inadequacy of the original experiments.
Yeah, actually, like one thing you mentioned there was that, like, we do often have a sort of bias toward the more recent result. Like, if two results disagree, we tend to, for better or worse, think that the more recent one is like more likely accurate. And maybe in some cases that's right if the methods or tools have improved or whatever. But broadly, if we just have discordant results, you shouldn't think that
But that in fact is the key. So Wakefield produced his results about autism and the MMR vaccine. Of course, he had falsified his data, but before they got to that realization, they went back and they did further studies, but used larger sample sizes and much more rigorous methods. And it was because of the rigor of the experiments that they were able to say, no, this is deeper evidence. This is what allows us to exclude the earlier result as incomplete and gives us confidence now that we have more data, deeper data, and this gives us more confidence about isolating where there was an error in the original conclusion or the justification.
Right, good. Yeah, wasn't the original Wakefield study had like a sample of 12 or something like that?
Well, it was always a clinical study. It was, just suggestive. It's a tradition in medicine, and it's legitimate. But that's one of the reasons why everyone demands large-scale clinical blinded trials, et cetera.
Right, especially when it's discovering something new or surprising or of a significant impact, as something like that would be for sure. But yeah, I guess. You do mention, you brought up that term deeper evidence there, and how we can have, that's maybe not just about the quantity of evidence, but the quality of it. So how is that, would you say, useful or perhaps even critical for overcoming or resolving errors?
Well, in a lot of cases, it's that these, by developing more evidence, like the search for the W boson weight, creates new data that allows us to compare with earlier data. So sometimes that is as simple as the sample size with the Upsilon particle, or the discovery of the data on Avastan and its safety. In some cases, it's checking out new domains where you haven't tested the theory yet, but you presume it to be the case. So that would apply to the case of Boyle's law, where it was only after the original thing that they began to say, oh, now we can produce, because of new technology, cases where there are high atmosphere things, or because of these pressure things, we can create low temperature environments, lower than we can achieve just by going out into nature around us. So technology can have a major impact. In the case of the Hubble constant, it was the new technology and the higher resolution of the telescopes that allowed them to differentiate the two different kinds of Cepheid variables, or to differentiate the Cepheids from the nebula. So having that increased resolution from new instruments, new technology can do that. And of course, in some cases, it's just happenstance. Some collateral knowledge develops, and that allows you to see the solution to a problem or a solution to a problem that just hadn't been done before. So Newton created a formula for the speed of sound based on his mechanics. It was all appropriately deduced from first principles, but even in Newton's time, it was off the real value by at least 15%. So the mathematicians during the next century, I mean, some of the real greats, Euler, Lagrange, etc., worked hard to try and resolve this problem. But it wasn't until there was discovery of adiabatic phenomena based in part on new technology that allowed that phenomenon to be created and then observed and then measured appropriately, that Laplace was able to say, oh, this might account for the fact that the air is expanding and contracting as the sound wave is going through because the temperature of the gas is changing. And when he cranked through the mathematics, lo and behold, he was able to come up with a revise Newton's erroneous formula by adding factors that accounted for the adiabatic phenomenon. So collateral knowledge in that case, you just needed to know about adiabatic phenomenon before you could fix that.
Right. I was just thinking about something like, I sometimes wonder about, because a few months ago I talked to Daniel Whiteson, and he has a book about alien science where he sort of explores thinking like, well, what if there were aliens doing science? What might that look like? And how, if we were to get contact with them, like what might we expect? And so thinking about that, and here I'm sort of thinking about like, to what degree are the theories that we've developed and the way we go about developing them specific to us, are also partly accidents of history, things that even given the way we are could have easily gone different ways. And I wonder, maybe those wouldn't introduce new errors per se, but I don't know, something that I'm thinking about that might be relevant here. Do you see what I'm getting at? Like these broader facts about us and our history and so on.
Yeah. So fresh perspective. I mean, there's a whole realm of thinking about mavericks and heretics and iconoclasts and their contributions to science. Sometimes they're wrong, but they might be contributing something important simply by bringing a new perspective to bear and getting us to check something more deeply. That is going to be, of course, in balance with the fact that if it's totally unimaginable, we'll have no way to leverage our way to produce evidence or understand it properly. So in some ways, the history of science is path dependent. We build our new discoveries on the old ones, whatever they happen to have been, even if we destroy them later on. We trust Newton. He said that atoms were held together by an analogous force to gravity, called them chemical affinities. Well, we don't believe that now. But we did a lot of work based on that. So I don't think we can hold ourselves to some imaginary ideal like we can think objectively and imagine without any of our known benchmarks. But that doesn't mean that we can't leverage our experience to find out new things, particularly when we have people who have different experiences, different observations, different theoretical interpretations. And through discussion and sorting things out, we say, oh, well, yeah, Mr. Kelvin, that was an interesting way to approach the age of the Earth, but we're going to work on other ways as well.
Right. Yeah, okay. I did want to briefly cover stuff you say about bias a little bit, because like we've talked about confirmation bias already and bias more generally, and you might think that, or someone might think that that's always something that's bad, right? Something to be mitigated whenever you can. But as you discussed, sometimes biases are useful or even good. So like maybe if you want to talk about that, how there can be useful biases, but also how we want to mitigate it, especially when it comes to epistemic hubris and stuff like that. So I don't know if you want to talk about that.
Yeah. So it's interesting when scientists in particular talk about bias, they always talk about it in a negative way. Sackett has a definition which is widely appealed to. And the very definition says something which takes you astray from the real result. And that can be true, but that doesn't mean that having a certain perspective or thinking in a certain way might also be productive. So we champion Michael Faraday for his discovery of the electromagnetic induction, the discovery of the motor, etc., without always giving an appreciation of the fact that he was deliberately looking for unity between the forces of nature because of his religious sect, a small group known as the Sandemanians. So he saw harmony and unity in nature and made an important discovery. At the same time, he was convinced that there was going to be a relationship between gravity and electricity. And he made many excursions into looking for the gravimetric effect. Not succeeding, he came back to it later and tried again. Those were all errors, ultimately. Perhaps if you didn't commit to them, but he seemed like pre-committed because of his bias, that it was there. So we might, at least for Faraday's own sake, say that that was an error. And again, methods which work on one occasion need not necessarily work on another, even though we think that they are exceptional. So new chemical spectra of compounds helped us discover rhodium and scandium, thallium. And they also helped us discover coronium and nebulium from looking at the spectrum of the corona of the sun and the spectrum of, I think it was the Cat's Eye Nebula. And it turned out, well, although they were put on the periodic table and adhered to for quite a while, those particular elements proved not to be the result because, again, collateral knowledge that they didn't know that you could have highly excited states of elements beyond temperatures that were known or beyond excitation levels that we're familiar with them. So here we have cases where people are using these methods and they're making errors sometimes, and they're making discoveries on others. And if we get rid of the biases, then we get rid of, in a sense, our ability in some cases to make discoveries. So we should be acknowledging that the cost of discovery is the possibility of error. It's kind of a interesting way of thinking about the fact that nothing is guaranteed, and we know that, but we're often not willing to acknowledge that we're going to encounter errors, and that's part of doing science. What matters is how we manage them.
Yeah, so that's a way to make progress through error, I suppose. Just thinking about the bias just a little bit more, though, like, yeah, it does seem like a very, at least broadly, beneficial thing to have at small scale, maybe individuals or small groups of individuals having various biases that lead them to explore different things that otherwise they might not have explored were they not to have those biases, or were people to be generally having the same biases. But that, yeah, you'll probably have a lot more errors or dead ends, at least on small scales, but broadly, you're more likely to get important discoveries, sort of, as you say. And that might be worth the cost of sometimes wasted energy or more errors that you might have otherwise gotten. Yeah, so that seems...
So, I mean, this is partly a theme that was addressed by Kuhn under the label of the essential tension. In what ways do you tend to have everybody work together and make progress by agreeing on one particular paradigm? And to what degree do you make progress by bucking the trend and pursuing an alternative paradigm? And Kuhn recognized, and I think anyone who looks into this, is that it's a payoff, and there's no guarantee. And we can say the same if we look at organisms and how species adapt. Natural selection is another process of change and adapting to new environments. So the structure of variation within a species might tell us something about how rapidly it adapts, how dramatically it adapts to large changes, so having, as you said, a distributed population structure where you have one species but with lots of different populations working in different local environments, different variations, means that if one particular local variation fails, another may flourish. So there are lots of interesting metaphors, I think, in evolution, which evolutionary epistemologists and philosophy, I'm sure, are more than willing to exploit.
Right. But also, I should have mentioned another thing that comes up when we do have all these errors, that still can lead to a sort of kind of negative knowledge, which you think is important. It helps us discover what's not true once we uncover the error. So I don't know if you want to talk about negative knowledge and how you think about knowledge and resolve for uncertainty and that sort of stuff there.
Yeah. So negative knowledge is, first of all, we have to sort of come to acknowledge that when we isolate an error, when we've done a controlled experiment to say that this is the source of error, this is why we got this particular result, that conclusion is justified, that this is, this misled us. In fact, the Viceroy butterfly is not a Batesian mimic, it's a Mullerian mimic. The data now on, testing the birds shows that now. That's an important bit of knowledge to know, in addition to what we learned by revising our knowledge. We've already talked about leveraging that knowledge to recognize other errors, to create these error repertoires, and one of the ways in which those error repertoires can be valuable is by escalating standards of proof. So when Svava Ipate was working on the Neanderthal genome, there were all kinds of ways in which the DNA could get contaminated, or in which the process of determining the genes could be mistaken. And they started out with some historic studies that had been done in Quagga and some, I think, Egyptian mummy samples, and used those, but then they developed methods around them to say, oh, but we can safeguard against that particular error. If there are short fragments, we can look for overlaps in the fragments and then build larger sequences based on the overlaps of smaller fragments. And as you watch the history of his research, you see he's encountering more and new errors along the way, but in each case, he's finding a way to get around them, giving him confidence in the results. And to me, creating the Neanderthal genome was a technical tour de force based on overcoming errors by recognizing them. And for me, at least, That's why he won the Nobel Prize, or was at least worthy of it. Not for just having done the work, but for having surmounted all these various errors along the way. Those errors were all very, very specific to his research in extracting DNA from fossil samples. But in some cases, learning about these errors leads us into much more general things. So if we think about the modern, we've already talked about the importance of the modern clinical trial, double-blind studies. We can, in a sense, pinpoint historically when this method was developed. Adolf Bingel was studying the effect of sera as a clinical treatment, and they already knew that about the placebo effect, so they had to blind the patients. But Bingel had heard from other reports that the physicians who knew which patient was which might be biased in their diagnosis of the progress of that patient based on whether or not they had gotten the sera. So he introduced another level of blindness, not letting the other doctors, even in his case, even his own patients, know who had received the sera and who had not. So that was aware that you could make these mistakes. They developed a new technique. So if we think about all these methodologies that we have, we can track down the history of the controlled experiment. We can track down the history of calibrating instruments. All these methods are historical results of errors. And we've already talked about the fact that there are publication biases. And acknowledging that those are errors, we're now in the midst of creating new methodologies in publishing protocols, in review protocols, search protocols that allow us to overcome these particular problems, because in some cases we can't eliminate them entirely, but we can learn to manage them. So these are multiple ways in which errors, although we had to struggle through them initially, can be leveraged to help us conduct science better in the future, better methods.
Yeah, good. And before, I do want to wrap up in a few minutes, but yeah. I did want to ask about, because like one worry that someone could have, and it's a known argument in the philosophy of science, is that, look, there's just so much error, right? Especially and including in theories that have had widespread support. And what we might worry, and this is called the pessimistic meta-induction, probably our currently accepted theories have errors as well. And so maybe we shouldn't accept that our current theories are true or even approximately true. What would you say about this worry about, well, I guess pessimistic meta-induction in particular, but like just the, I guess, broader worry that there's just so much error in science?
Yeah. So there are in a sense, I think, two lessons to take away. One is people seem to think that if we've found an error, we've thrown away the knowledge, and that therefore we've lost something, and that science really isn't progressing. If, as we've been talking about, the knowledge of an error is a form of knowledge, we can count that as something that we know. That's a conclusion that we might have reached, but we know not to because of this other consideration. Those in turn escalate our standards of proof. And that's an interesting concept, which I think it may be coming out in another book sometime later this year, that if you've escalated your standards of proof, your knowledge is better. Why would you have wanted to keep knowledge that didn't meet those standards? So yeah, you threw it out. It's a loss at some level, but not necessarily a loss overall, because what we have gained is better knowledge through appreciating the higher standards that we needed to meet. So these are ways in which we can view science as progressive by incorporating both the positive knowledge and the negative knowledge and escalating our standards of proof. We're still left with the notion that, no, we haven't discovered everything. There's always something possibly hidden around the corner. And that's why talking about these limits to our knowledge, the qualifications, how deeply have we probed this? In what ways have we checked it for possible sources of error? Those are all ways which increase our confidence and, in a sense, allow us to apply that knowledge within the domains of those particular qualifications. And who cares if somewhere along the line we find something else or there are some exceptions? If we're careful, we work within the scope of what we have. One of the things I've been thinking about lately is the ways in which skepticism is leveraged in the media just to destroy scientific claims. And this kind of Cartesian doubt of, I wonder if, well, I'm not really sure that's true, is very, very corrosive. And I think one of the things that we learned in the late 60s and 70s was that when theories change, sometimes there's revolutionary upheaval, but you have to have something better to replace it with, or you just don't abandon something without having something better. So in some ways, the pessimistic fallacy is this kind of broad-based skepticism that doesn't leverage any other knowledge. It just leverages skepticism. And in that sense, it's very asymmetrical. And you say, if you don't have something better to offer us, don't bother. Wait until you have it. And when it comes along, we'll manage it. That's how science works. The cost of discovery is the risk of error.
Right. And that sort of, I mean, you talk in the book about how you want to sort of naturalize error, and I guess that's what you're getting at there, right? That we shouldn't treat it as a sort of necessarily something that's to be avoided at all costs, or that it's like a terrible pathology, or however you describe it. But it's, and as you say, part of the path of discovery.
It's part of the process, and it has nothing to do with how good a scientist you are, because no one's going to impugn Newton for having made the wrong formula for the speed of sound, or for having proposed chemical affinities. No one's going to malign Galileo for having based his whole book on this erroneous theory of the tides as proof of the Earth's motion. And I've written about a number of Nobel Prize winners who, made mistakes. They can win a Nobel Prize and they can still make mistakes. That doesn't impugn their quality as a scientist. That's part of the process. To err is science. It's what we can say. But also, finding and fixing errors, that's also science.
Right, of course. But all that can lead to progress, and often doesn't has. So, yeah, I do. Well, no, that's not even just leading to progress, but that is a form of progress too, finding the errors or identifying the errors and then correcting them and so on. So I do normally end these interviews with a kind of general, kind of meta-philosophical question. So maybe we could talk about specific to philosophy of science, and then maybe more generally if you want. So what do you think is the value of philosophy, or maybe in particular philosophy of science, to yourself, or more broadly to, why is it worth doing, do you think? And maybe a broad question, but I want to see what you think.
There might be a metaphysical dimension to that. And I come out of originally a background in science, so I'm very pragmatically oriented. So I am a proud member of the Society for the Philosophy of Science in Practice, and at least most of my work and how I conceive the work of the philosophy that I do, not exclusive of other avenues, is how does this help us understand the process of science more deeply? Can it help us refine our scientific methods by articulating them, generalizing them, clarifying them, and, for example, using philosophical analysis from the histories of errors to identify what those new methods, buoyed by a philosophical analysis, might look like. So I'm very much of this strategies part that comes out of, I want to say, University of Chicago, Darden, Wimsatt, Bechtel, among others, that says, how does philosophy concretely enhance our practice of science and indirectly our understanding of science for those of us who consume and use science? So not much metaphysics in that, very instrumental, but I think it's an argument that can be tangibly made, particularly with reference to history.
Yeah, no, it makes sense. I mean, if anything, you could think of some of the philosophical work in this book and sort of related thinking about philosophy of science. That's something that can contribute to our scientific practices and other epistemic practices more broadly, perhaps. And that's a value right there, if at least a practical one. So, yeah, I'm sure there's more than that, but yeah.
David Hull's whole career was based basically on meta-science, treating philosophy as the science of science.
Yeah, I think it's good. At least the philosophy of science is the science of science. I mean, maybe we want philosophy to be more broader than that, but I don't know.
Oh, absolutely. There's that's not necessarily going to answer ethical questions, but for the sake of science, philosophy is a version of the science of science, and in particular, using the study of history and sociology of science as data, as evidence for not just imagining results, but really testing them against our experience.
Very good. Okay, so I think, we've been going for almost 2 hours now. So we'll end the questions there. But yeah, thanks so much for coming on and Dr. Allchin and taking my questions and writing this book. It's been very fascinating getting to read and having you on to talk about it and getting your answers to the questions. But it's been really great having you.
It's been a great conversation.